Now we have the talk by Professor Ashish Awasthi ji from NIT Calicut. Professor Awasthi has already taught you about MATLAB program for root findings, interpolation and extrapolation, as well as about the matrices and numerical integration. He delivered one talk on day 4, and another he delivered a talk on day 5 about the Runge-Kutta method for solving the equations, nonlinear algebraic equations. And today Professor Awasthi will be talking about the maximum principle and convergence, and also about the von Neumann stability analysis method. So with this, I welcome Professor Awasthi to the day 7 of this FDB. And I request Professor Awasthi to start his lecture. Thank you.
Okay, thank you, Professor Rahul, for your introduction, and good morning, one and all. So today is, I think, that concluding day for you, and today we will be talking about the von Neumann stability. Okay, before that, we will talk about the maximum principle and the convergence. So let me share my slides. Am I audible to all? Yeah, please write it in chat box. Okay, fine, thank you. So we will be now starting today about the maximum principle, convergence, and von Neumann stability. So as you have already seen a lot of lectures on basically numerical methods for solving the differential equations, especially the partial differential equation. So now we will be talking about that when we are solving a partial differential equation, and how we are ensuring that this particular method, okay, when you are solving by any numerical methods, it could be finite difference or it could be finite element. How would you ensure that this numerical methods will give you the results which are the true results, okay, or maybe close to the true results of the differential equation? And if you have the exact solution, you can easily identify that by comparing the numerical results by the exact results, right? But there are a lot of problems which do not have any solution, isn't it? So how do we sure that this particular method is going to give you the desired or accurate results, isn't it? So we will talk about the stability. Okay. So before going to the stability, I'm just see that there are various ways to ensure about the stability. Again, I will just recall that what is the stability. Okay, stability means what? So you know that it is a general concept that stability means that if you make some error or you give some perturbation to the system, it could be a numerical method system, or it could be analytic method system, or it could be any physical system, isn't it? So you just make some artificial disturbance, okay, artificial disturbance, you can make it, and see that after that giving that disturbance, how this system is going to behave in regard with the giving disturbance, right? So if the system is behaving, suppose you have given a small disturbance, and system, whenever system is there, yeah, it may not have the much changes, right? So suppose there is a system, and you have given some disturbance to the system, and you have checked it that the output or the behavior of the solution of given by the system is also having the small disturbance, or small disturbance or no disturbance, right? But if it is other way, that for example you have made small changes and you have found that in the solution output there is a big change, isn't it? Then we can say that this is not the stable, isn't it? And that day I gave the example for our like food habits, right? So when we buy grains or we buy vegetables from the market, so we will first job is that to make clean it, isn't it, by washing, and then still a lot of entry nutrients are there. Again, we want to minimize it by cooking, etc. So why we are doing exactly? We want to eat it that, right? And you see that still some people will get disturbed because the stability of our body, okay, that depends that if small changes are there, a small amount of pollutants are there in our food, isn't it? If we are healthy, we don't have much effect, isn't it? Or we have no effect, isn't it? Because our health is okay. So it's kind of an instability, right? But if you take, for some people, if they go and eating habits little bit here and there, and you see that their stomach will be upset or they may have the illness, isn't it? So you can say that it is not the stable system. Same thing with the numerical methods also, or you can say the same thing for the, if you look at the civil engineering, right? When they are constructing a bridge, isn't it? A lot of vibrations, everything is happening when a car is passing or train is passing, isn't it? So you see that they will do the testing in the beginning itself by making the small amount of disturbance, and see, they will see that what is going to happen to this system when you make some disturbance. So what I want to say is that if you want to ensure about stability, you have to give some disturbance, and with that disturbance, we want to see the behavior of the system, isn't it? Fine. So that is the stability. Okay. Now there are various ways to ensure about the stability. One of them is the maximum principle. Another way is the by using the von Neumann methods. We will discuss about that. Or you might have seen that there is another way. It is called the matrix method, isn't it? Matrix method, that I think Dr. Vikas Gupta might have taught about that particular method maybe yesterday, right? So here we will discuss about the maximum principle. Maximum principle is a very fundamental thing or very important thing in connection with the partial differential equation, isn't it? Because it will ensure something which is really required, isn't it? So you look at that, it is written that the maximum principle is a fundamental qualitative property of solution of many partial differential equations. Okay, and it tells us about that what is the maximum value, what is the minimum value, isn't it? And what about the solution? Because when you know maximum, when you know minimum, that means you can say that the solution is bounded. So boundedness also you can find it out, and you can say that there is a fixed maximum, there is a fixed minimum, then the solution is also bounded. So boundedness is preserved. Okay. And through that, we can predict the stability of the numerical methods in terms of the numerical methods. Okay. So stability of the numerical methods can also be identified by using the maximum principle. Okay, especially for the heat equation, that is the time dependent problems, isn't it? Time dependent both problems, like it is there, and then there could be time independent problems. Okay, for example, elliptic partial differential equations, Laplace and Poisson. Okay, and it will also tell about the physical interpretation of stability, because solution cannot grow beyond the certain bound. So you can find it out that when you have a physical phenomena, if you look at that, if you do modeling of that physical phenomena, for example, turbulence model, right? If you have a turbulent model and you have a correct Navier-Stokes equations, partial differential equation, along with some conditions, isn't it? Okay, if you apply maximum principle on that, if the modeling is correct. Okay, first of all, turbulent models are itself is a doubtful thing, isn't it? So if they are correct, in that case, you can find it out that what would be the solution of that particular model. You may not be able to find exact solution, but you can find out the boundedness of the model. So you can say that the maximum speed or maximum thrust, that depends on the model, which model you are having, turbulent model. So you can identify that how much maximum thrust could be there, how much maximum speed could be there. Okay, just by analyzing the concept of maximum principle. So now let us see. We will start with a simple example and see that how this maximum principle will help us. Okay. Now go to the exact the maximum principle. Suppose let us take the heat equation, right? This is the simplest second order partial differential equation. This is a parabolic problem, as you know, right? Here you can take alpha as a positive, and left hand side is a temperature gradient, and the right hand side is basically a Laplacian. Okay, Laplacian. So it's a second order diffusion term. So this is also known as the diffusion equation. This is also known as the heat equations. Okay, and mathematically it is known as the parabolic problem. And this problem associated with the initial condition that I have not mentioned here about that, but there should be some initial condition because the time dependent problem. There are two types of the time dependent problems are there in the partial differential equations. One is parabolic, another one is the hyperbolic, isn't it? So heat equation and wave equations, they are the most popular known as the time dependent problem. While if you look at the Poisson problem or Laplace equations, they are the time independent problems. They are only problems which will not having any initial condition. They will have only the boundary conditions. But for the parabolic problems, you have the initial condition and as well as you have the boundary conditions. Isn't it? It's interesting. So that is the reason that time dependent problems have a little bit higher order of challenges in the sense that it will have the initial condition, it will have the boundary conditions. While if you look at the time independent problems, for example, elliptic problems, okay, Laplace or Poisson problems, they will have only the boundary condition. They don't have any time derivative, isn't it? But practically, if you look at that any physical system which is depending on the time, and you see that in the current in the universe, all the models, isn't it? They may be directly or indirectly affected by the time, isn't it? So that is why parabolic and hyperbolic systems are more and more there in the modeling of engineering problems, isn't it? So it will have the initial condition, it will have the boundary conditions. You can say that there will be one initial condition and two boundary conditions for this particular heat equations. Okay, altogether you can call this as a initial boundary value problems. What about the maximum principle? So maximum principle here, I'm just telling in a very short way, okay, very clear cut way, that the maximum value of the solution. What is the solution here? U. Okay. If it is a heat equation, you can say that U is nothing but the temperature. So it occurs either at the initial condition, at the initial level, at time t equal to 0. Okay. It will be defined through that whatever the initial condition is there, through that you can say that maximum may occur on the initial condition or at the boundary conditions. So it is written that at the initial time, suppose if it is t equal to 0, it could not be t equal to 0. If you are taking some other initial time, it is absolutely fine. At the initial time or at the boundary of the domain, isn't it? Boundary will be at the x, right? So x domain. So they are telling that it will always be there with the boundaries, right? So it is not going beyond the boundaries. I think I'm unable to write on it, or shall I write it here? Okay. So I'm writing, I'm not getting the pen here. Okay, fine. Now I'm getting the pen. Okay, fine. So here, if you look at that, the initial condition will be like this: U at x comma 0. Okay, this is the initial condition, and the boundary condition will be on like this: a comma t. Okay, something, and u b comma t. For example, the domain is a to b. Okay, so I can call this as alpha. For example, this is beta. Alpha already there, so alpha 1 you can call. and then here something will be there. I can call suppose f of x, or it is a fixed value, for example, let us say n. So the maximum or minimum will be here between these. Okay. So you see that without solving the problem, you know that the solution will be somewhere in between the maximum, whatever maximum value are there. If it is a constant, if it is a variable, you have to identify will be there in the using the initial condition and boundary conditions, isn't it? Here you can use the reverse engineering also. Suppose you want the solution which is bigger than that, you don't have to change the equation, just you change the initial and boundary conditions, and then your bounds of the solution will be changing, right? So you see that by using the maximum principle, you can do a lot of things regarding the solutions also. Okay. And what is the physical meaning? Now, physical meaning is just telling that heat cannot spontaneously increase inside the domain, isn't it? That means, because heat means that temperature, right? So basically U is the heat. Here U means it is heat. So it will not give you the unbounded. It is not increase inside this spontaneously. So it will increase in the bounds, whatever bounds are there, maximum or minimum, isn't it? So it will be under control. So you see that if you have a physical system which is described by the heat equation, you have a full confidence because of the maximum principle that it is going to behave under these bounds. And solution is controlled by initial and boundary data, because they are the bounds. So you see that the maximum principle basically is behaving, is telling, actually, it's not the anything new. It's something like that. It is telling that initial and boundary condition will define the bounds of the solution, isn't it? So the solution will be controlled by initial and boundary conditions. It's interesting. Okay. So that is the beauty of the partial differential equations. You see that you might have studied that partial differential equation and ordinary differential equation. Partial differential equations, actually, a lot of things are depending. Even ordinary also it is depending, but in partial differential equations, actually, is fully controlled by the initial and boundary conditions. Okay. Even there is a method which will work on certain boundary conditions, but the same method will have the difficulty with the another boundary condition. For example, if you are using the separation of variable with Dirichlet boundary conditions, isn't it? You can easily find it out, and that also homogeneous part, right? If it is a non-homogeneous Dirichlet boundary conditions, separation of variable becomes tedious. You have to convert a non-homogeneous boundary condition to the homogeneous boundary condition. Now, if you talk about the Newman conditions and you are using separation of variable, isn't it? It's going to be big challenge. So it just, what I want to say is that by using the initial and boundary conditions, you can play a lot with the methodology of solving the problem, and of course through maximum principle you can also say that the control about the solutions, isn't it? So will be defining in that. Yes, correct. Okay, so another one, this is actually maximum principle which I have tried to give you, which is for the continuous problem, and the similar things will be for the Laplace equation, because here this is time independent problem and this is the Laplace equation. Okay, and here only boundary conditions are there. So Laplace equation will have only the boundaries. Okay, this is only having the boundaries. Right, so condition will be here, condition will be here, condition will be here, condition will be here. So maximum will be there on the boundary, isn't it? So it will help us about the boundedness. So that is the region that it is there. It is telling about the boundedness of the solution. Because you see that whenever we do any physical things, we always bother that it should be under control. When you are driving a car, right, we are always try to make that we can make the speed as high as possible, but it should be under control. But once control is lost, okay, that system is totally wasted, isn't it? So all engineering system, or you can say physical system, should be under control, especially if you are designing system, isn't it? So how to ensure it? By using maximum principle. And what maximum principle is telling that system, whatever you are creating, it is fine, but make the boundary conditions finite under your desired limits, so that the solution of that system will be controlled. Okay, now because we want to do for the numerical method, so it has a discrete version. Okay, so discrete version of the maximum principle. So it is known as the discrete maximum principle. In the short form, you can call this as a DMP. Okay, what is DMP? So the DMP is again, it's again a similar modified version of the maximum principle. You see that more challenges comes. So suppose you have a partial differential equation, could be a parabolic, hyperbolic, or elliptic. Any problem is there. Now what happened when you have applied any numerical methods? Could be finite difference, could be finite element, or any method. What happened actually? You have actually just removed that continuity things, and you have make everything in terms of the numbers. Okay, numbers. So they are the numbers. When you write the code, okay, even the first line, when you see that, it is nothing but the numbers. Now you have actually broken all the continuous problem into the numbers. Now these numbers will grow like, sometimes depends that what is the error is there, and also it may be difficult to control it, right? So how to ensure theoretically that whatever the breaking is there, whatever the discretization, we can call this as a mathematical terms is discretization. When we discretize, what is the discretize actually? According to me, that the continuous derivative, you are breaking into the numbers by using the Taylor series, right? So now these, whatever you have done, the procedure or making the discretization, so that discretization you have to ensure that it will give you the required things, isn't it? So at least the bounds of that solution we can again do through the discrete maximum principle. So what discrete maximum principle is telling that, if you read it, it's clearly very crisp way we have written it. A finite difference scheme for a partial differential equation satisfy the DMP if any time label, the maximum and minimum value of numerical solution occur either at the initial condition or at the boundary nodes. Can you let's see what he's writing? Is alpha fixed? Yes, we have taken alpha fixed. You can take the function of x also. Okay, it is fixed for heat equation. I mean, there is a condition on alpha. Alpha should be positive. Okay, just because, see, thing is that now we are not, I'm not teaching you the existence and uniqueness that also can be ensured by maximum principle actually of the partial differential equation. You know that when you are a mathematician, now suppose you have a problem, isn't it? Cooling problem, heating problem, anywhere, isn't it? Now, for example, nuclear reactor, let us say. Now you know that how much heat will be generated. So when you have done the modeling part, okay, as a mathematician, we should ensure that whether this has a solution or not, isn't it? Accordingly, the model we have to modify, because if it has no solution, we cannot work with the numerical methods, right? So it should be having a solution. So for that, the heat equation also can be treated that whether it goes all things, isn't it? So alpha positive you can take, but it can be a function of x also, isn't it? Fine. So let us come back and see that here about the DMP. Okay, so DMP is same thing. DMP, what actually, for example, if you are using the finite difference, it's a very interesting thing. So suppose you are using the finite difference, you have the initial line. This is the initial condition, right? And suppose you are doing heat equation with under the initial and boundary condition. I am assuming that all are constant, isn't it? So now this is your initial condition. So you have these nodes, right? They are the value coming directly from the initial condition. You have the boundary condition. So this is, I can call this is the basically zero time label, right? Or first time label if you want, you can call this. I'm calling this. And then through that, you can calculate the first time label. So in general, you can call this is nth time label and this is n plus 1th time label. So solution here I can call as a un, and solution here I can call that as a un plus 1. Okay, you can put j or whatever it is. So as per as maximum principle or DMP, it is telling that the solution will be either here or either will be on the boundaries, right? So that means that at each time label, your solution will be bounded. You don't have to check, isn't it? Because maximum principle is telling that the maximum value of the solution will be either on the initial condition or at the boundary condition on these lines. Okay, so these lines, I'm putting this as these lines will have the maximum values. So whatever solution comes at each time label, when you are progressing, you see that you don't have to worry. It will never grow. Why it will not grow? Because if you have a fixed boundary conditions, okay, or you have a finite boundary conditions, or you have a bounded boundary condition, I can say that if it is a variable, then your solution at each time label will be behaving nicely. It will be always bounded. So free from your worries, you just do simulations, you proceed from first time label to second time label to third time label and so on. So you can easily go from NH to N plus 1, NH to N plus 1. Easily you can go for N 0, 1, 2, 3, 4, 5 as per your desired. It will not grow. And that is happening when you plot the heat equation. You see that when you progress in the time, isn't it? You will reach to the steady state, and the steady state solution will be coming. Okay, when you increase the time. Okay. That depends that what type of the problem. If it is heating the rod and the source is removed, you see that the temperature will come down, and it will be stable at the room temperature. Okay, by simulations you can show it. Okay, and you can say that because of the maximum principle, or not because of the maximum principle. The property is there for this heat equation, okay, which follow the maximum. So maximum principle is a very interesting and helpful tool actually to analyze certain properties of the solutions, isn't it? One of them is the boundedness, and it will help us actually to ensure about the stability, isn't it? So this maximum principle nowadays we are using as a tool to ensure about the stability. So now you see that the key properties of the DMP, it will help us to ensure about the stability. It will ensure about the boundedness. It will say about the physical realism. Okay, no spurious overshoot or undershoots. So no spurious things will be there. It will not be sudden changes, like it will not be overshooting or undershooting. Overshooting means it will not increase randomly, it will not decrease randomly. Okay, gradually it will happen. And suppose if you feel that any numerical system, if it is not following the DMP, what will happen? That it may lead to the instability, it may lead to the non-physical oscillations, and so on, isn't it? So you please note that this is again one-way traffic. If we are telling that if any numerical method satisfied the stability things, isn't it? Whether it is satisfied the discrete maximum principle, or in future we will do the von Neumann stability and all. We are ensure that this physical system will not be having the randomness. That means it will not create the overshooting or undershooting, isn't it? So we can say that whatever solution will be there, it is under the control. But question comes, suppose if it does not satisfy, then it is not telling. Please note that it is not telling that if violation happened, isn't it? Violation happens. Suppose discrete maximum principle is you have designed a numerical method, which is not a traditional numerical method. For example, you can design a numerical method which is based on the non-standard finite differences, which you have not studied, but somebody might have heard the name non-standard finite difference. Again, again, people are working on it. So there you see that because the derivatives are not coming from the Taylor series exactly, the denominators are not like this h or k or maybe delta x or delta t, something different also you can choose. So in that case, this maximum principle may not be applicable, or DMP may not be satisfied directly. Okay, so we can't say that it will not be stable. We can't say that it will not be bounded. So we will say that if it is not satisfied maximum principle or DMP, we will be silent, but we cannot give you the guarantee. It's like that you see that when you buy a car and something goes wrong and you go to the local workshop and you have done something alteration, and then company will say that I am not responsible. But they are not telling that it may lead to damage of the car, nothing like that. But they said that I am not responsible. Same thing here. If DMP is not satisfied, we can't say it may be stable, it may not be stable, it may give non-physical oscillations, it may not give the non-physical oscillations. We can't say anything, isn't it? The guarantee things will be removed, isn't it? For some values it may work, some value it will not work. So randomness will come in the numerical systems if it is not DMP. But please note that violation of DMP does not imply that it is always unstable. It is nothing like that. This is very important actually when you go for the research, isn't it? So you have to understand all the concepts, especially in the differential equation. They are in the one way, isn't it? Because when I teach the differential equation, just I am sharing my experience. For example, ordinary differential equation of order 1. So when we talk about that, existence and uniqueness. So we will say that it's a big theorem, existence theorem and uniqueness theorem, and it will ensure about the solution and the uniqueness of the solution. But what will happen if it does not satisfy the existence theorem or does not satisfy the properties of the uniqueness theorem? What will happen? Will it have a solution or will it have no solution? So again, we will say that if existence, uniqueness theorem, whatever is stating, if those are satisfied, we can say that it will have a solution and this solution will be unique. But if it does not satisfy, we will be silent, like we don't know. It may or it may not. There is no guarantee, but it may have also. So it's a one way. So many times what happened in the numerical methods or in the differential equation or in the life also. Suppose somebody will study hard. Okay, there is a guarantee that he will get a good grade if he is really working hard, isn't it? But if somebody is not working hard and not studying properly, but we don't know, isn't it? He may get or he may not get. Don't know. We cannot say that he may not get, isn't it? Something like that. Okay. So we have limitations, so we have to be a little careful about that. That's it. Okay. Now here I am going to talk about the stability. So again, I will say that I have already told that in a simple numerical method box. Now here something is there, we call it as an input and something will be out. Okay, and what is input here? Initial condition, boundary condition, these are the inputs basically. Okay, so when you give the input and you make some changes here, you can make some disturbance, you make some perturbation. Perturbation means changes, disturbance. Okay, now when output is there, this disturbance, or in engineering they call it as a noise. Okay, mathematically we can call that as an error. We make some error here and see that our output, if it is a small error, and output also may have a no error or a small error, we can say that this is stable. So, but if you make a small error here, put as a big error, then call it as unstable. In the real life also, you might have seen that. Okay, if somebody will say to some person, just small changes, isn't it? But output is going to be big changes. That means the particular system to whom you are telling is not the stable. Same thing here. If there is a small change in the input, will leads to the no change or small change in the output, perfect. Otherwise, it is going to be a problem. It is not the stable. Okay, fine. So this is the way of telling about the stability, isn't it? So that is what it is written, that a numerical method is said to be stable if a small perturbation, okay, in the data. Okay, this perturbation, you can say that I am very smart and I will not make any changes in the initial data or boundary data. But if it is a physical problem means that, for example, prediction of the weather. So data is coming from the atmosphere. When you take the data, your machine will not able to capture the perfect humidity. You may not able to perfect temperature. You may not able to perfect location, that humidity at this height or humidity at that height. All those things may be not very accurate. This is one way that sometimes initial and boundary data is not in your control. It is coming from the experiments. First thing. Second thing is that if you are making sure that theoretically that initial data, boundary data, make any error, right? Isn't it? In that case, how you will going to control about the round of error? Because finally numerical methods means that they are the numbers only. You look at that continuous problem, you have discretize it. Okay, make this as a numbers. This is discrete problem. So if you don't have anything, but still round of error is always there. For example, something divided by something, right? Automatically round of error will come. That day I told you that, for example, 1/3. Is it? How you will going to control that? You can't control it. You have to truncate somewhere. The round of error is generated. So these errors will be generated for every system. It is not in your control, right? So those errors also should be under the control. They should not grow. That is the reason that we are always worried about that the system should be a stable system. Otherwise, what happened if there is no error in the input data, or means initial or boundary, but still there will be something going on in the inside the system when you do the calculations, isn't it? So that itself will make some perturbation, some changes. So you have to make the system stable 100%. Then only you are going to ensure that the output, whatever it is coming, it is not having the growth of error. Otherwise, it will make something different. Isn't it? The actual solution is suppose 100 and you may get the 1000. So that will happen if your system is not stable. Again, I'm telling that no guarantee that it may not give too much difference, but we cannot guarantee. But if it is stable, 100% it is there for all the data. Okay, so that is the meaning of the stability of a numerical system. Okay, in other words, you look at that. These are the things. Actually, it's not the bookish language. We try to make in a more sophisticated and more understanding way, isn't it? So in other words, you can say that error is bounded. The solution remains well behaved. Well behaved means that nice guy, right? If a small changes, if it is boundaries are there, and through that only we can say it is a bounded. It is not going and giving anything random things, isn't it? So whatever we want, whatever initial condition, boundary conditions are there, accordingly solutions are coming. Okay, and the computed solution is not sensitive to the small disturbances. Of course, that means that suppose you have made little change in the initial condition or boundary condition, then again you have recalculated and you are seeing that the solution is coming almost the same, isn't it? There is no much changes. So you are sure that the method or the system which you have created is stable. Fine. Okay, so now we can say mathematically here actually it's again the way of stability that a numerical method is stable if every bounded initial data, the numerical solution remain bounded. Okay, so through the boundary data it is bounded, isn't it? So that means the solution again it is a kind of a maximum principle only. That is what restated here using this particular result. When you do the analysis matrix method, you might have seen that you have proven is that the solution at any time level will be bounded by the initial data. And you please note that when we say that initial data, because it is compatible at the nodes. So don't think that why I have not written boundary data. So I have considered here, this is the initial line, right? And you please note that this is also boundaries there. So I'm taking from here to here full, isn't it? So you can call this as initial. Boundary name you don't have to take because initial will have to satisfy this boundary also, right? It is called the compatible conditions. So initial data is enough. That's why don't confuse yourself. Again, I would say that any learning when you do with interest, isn't it? Do with the common sense. Okay, just try to understand and yourself, and again digest. Then what happens? You can solve even bigger problems also. You don't have to create the method something different, things which comes from the common sense only, isn't it? So that is what I understood, and I'm again telling to you also. You also try to understand this similar way, isn't it? Don't go that stability is something very different. Maximum principle is something very different, isn't it? by heart all those things, then what happened? You will not have understanding. Try to understand it. It is something like that. Okay. So when you are, you know that when you are starting coming from one place to other, for example, you are going to USA, right? Okay. You know that there is also everything is there. Like you know that, isn't it? Through some sources, know that if you are landing in the US or some other country, there is enough things are there. There is a place to live there. There is a market to buy the things, so your things will be satisfied, isn't it? So that's something like that only, isn't it? So so you know that when you are using this all maximum principle and all, you know in the advance before proceeding for the solution, that solution will be under the control. So that's important. It will give you the confidence, isn't it? So it's the common sense we are using all the time. So all the time we are using this common sense. When you are driving a car, you are sure that you have done enough inspection and anything. You are ensured that okay, fine. There is not chances are very less that anything is going to happen with that car. Brake is not working on what, isn't it? Because the initial conditions you have made it right. Similar things actually in the numerical methods also. It's nothing new. Okay. Now I'm not going to talk about that, but here it is stability in the continuous sense. Okay, in the partial differential equation theory. So if it is a continuous problem, stability ensures that solution does not amplify. It will not grow, okay, randomly, okay, and it is known as the well-posed problem. So maximum principle, another thing will ensure about the well-postedness also. And Hadamard has given the well-posed condition. What is the well-postedness? That the solution exists and unique, and the solution is continuously depending on the initial data. So this is the condition for the well-postedness of any partial differential equation. And before proceeding for the numerical solutions, isn't it? Okay, if this particular differential equation comes from a physical system, if it comes from the book, you don't have to bother. They are all well posted. But if it is coming from a physical system, suppose you are working in a project, okay, which is a project in some other department, for example, electrical department, civil department, okay, problem of a dam, isn't it? When you have done got the partial differential equation by modeling of the physical phenomena, and some conditions are there. In that case, being a mathematician, you ensure about the well-postedness by using maximum principle and some other theories. Okay, so that whatever numerical methods or numerical techniques you are going to develop will have the reliable solutions. Otherwise, we may not be able to get the proper solution, because there is no problem in the method, numerical method, but the problem itself in the modeling side, because the problem which you have model is not the having the well-postedness. So well-postedness is an essential condition actually to proceed for the numerical method. So that's why I have just written here. Okay. Now stability in numerical methods, especially in the time-dependent PDs. Okay. So stability controls the growth of error. Error could be like truncation error. It also will be under control. A round of error will be under control, or disturbances in the data, perturbation in the data. Perturbation in the data, I have already explained about that. If the data comes from a mathematical function, there is no chance of the perturbation. But if it comes from the experiments, okay, it comes from the what is called in some other experimental device, then there may be a chance that there is a error in the actual data, isn't it? So these things will be under control. So simple thing is that if it is a stable, error will be under control, a small error will be under control. But again, if there is a big error, it may not be under control. But we don't, because when big error is in the perturbation data is there, we will identify. Only we are not able to identify when a small errors are there. So those errors will be under control. And these are the property of the stability, boundedness, error control. And you see that many times you have seen that the scheme which you have given, rather than using the word stability, they will say that it is energy dissipation or energy conservative scheme, okay, or energy dissipative schemes, isn't it? Or non-oscillatory scheme, or it is a robust scheme, or it is a convergent scheme. Okay? These are the name of the stabilities. Various names are there. So the meaning is that boundedness means that solution stays finite at the time progress. That means that when you progress in the time from n to n+1, again n+2, and so on, when you keep progressing in the time, okay, you don't have to bother about the growth of the solution. Means whatever solution comes, it is under control or it is bounded. Okay, error control. When the solution is under control, error is under control. So it is not a different thing. Now next is that energy conservative property or dissipative property. That means the physical energy which is there in the system, okay, it stays within reasonable limits. For example, heat equation. So when we write the heat equation, that U is a temperature, that is a heat. Temperature means it is a heat. So you can say the physical energy, whatever there in the system, non-area, that means that no artificial oscillations. If suppose system is showing certain oscillation, that means they are really there in the model. That means in the physics it is there. When you have a heat equation, in reality it will have the similar oscillations. For example, you are modeling a problem which has the, for example, you are modeling a problem of oscillatory phenomena, okay, for pendulum equation. Okay, pendulum equation, or in engineering field it is called the oscillators. So oscillators has to oscillate. There is no other chance. If you are solving a pendulum problem, okay, pendulum problem, it is as such a simple harmonic motion problem. Second order differential equation, y double dash plus y equal to something, or you can call it a zero homogeneous form. So it will have the solution C1 cos something and plus C1 sin something. So when you do numerically also, this sign and pendulum itself oscillation only, isn't it? So that means that this physical has to be captured, but unless suppose there is no oscillation and it is giving oscillations, so that means it is here non-oscillatory behavior. So physical oscillation it should capture, but non-physical oscillations it should not capture. Okay, robustness, that means that meaning is that you might have seen that many places it is written that the method is robust. Okay, that is also in terms of the stability. Meaning is that in a similar class of problem it will work, isn't it? So works for a wider class of problems or data. And this actually we will talk about that. So when you have a numerical method which is stable, okay, how can we ensure about the convergence, isn't it? So if it has the consistency, then it will lead to the convergence. It is known as the Lax equivalence theorem, that we will talk about. So type of stability, like you might have seen already there in the differential equations courses. I think one day I have also seen that Dr. Shruti was talking about the absolute stability. So various type names are there. It's not enough actually, many other names also there. Absolute stability. In OD there is a stability also there, that's called absolute stability basically. L stability also there. So absolute stability bounded for all step size unconditionally. Okay, so that means unconditionally stable. Conditional means under the condition it is stable. Asymptotic stable, generally it comes from the theoretical side, not in the computational side. Theoretical side, you might remember that when you studied the system of linear differential equations, isn't it? Especially the homogeneous and non-homogeneous system. There you might have seen that this particular node, suppose this particular point, isn't it? If it is a node or if it is a spiral or center, whatever it is just asymptotically stable or not. That means the solution of the system when time becomes large, right? When t goes to large, whether it is going to decay or it is going to grow. So if it is going to grow, we can say that it is asymptotically unstable. When it is going to down, okay, then we call that it is asymptotically stable. So you see that when the solution comes in terms of the exponential, if it is e raised to power minus x or minus t, we are happy that because it is going to decay. That's the. So asymptotical stability generally we do for the theoretical systems, okay, not for the numerical systems. Numerical system, we can make the analogy by making the higher time, isn't it? So if you look at that, that's what I told you, if you simulate heat equation for a higher time, you see that it will lead to the steady state. After that, there is no change. So you can say it's a kind of an asymptotic stability arrive. Okay. Now, consistency. So consistency is not the part of this particular lecture, but I will just brief about that. See, three things are there: consistency, stability, and the convergence. Isn't it? They are the three key parameters to ensure about the robustness of the numerical method. So first of all, we will check the consistency. Consistency means what? Consistency means that when you have a heat, audible now actually, because today there is a failure in our department. So I'm using mobile phones. If somebody call or sometimes no internet data has issues, I may not able to connect the computer. Okay, am I audible? Okay, thank you. Thank you. So sorry for that, because our UPS actually is down today due to run here in Kerala. Actually, today is actually red alert. I hope that now my screen is visible. Confirm it whether it is visible or not. Okay. Three things actually, that consistency, stability, and convergence. So consistency means that when you have a when you have a differential equation in the continuous form, in the form of the derivatives, right? And by using Taylor series or by using some other approximation, you are converting to the discrete form, right? So now two problems are there. One is the continuous problem, another is the discrete problem. So how can you say that this discrete problem exactly same as the continuous problem, or it is a part of the continuous problem, or it is converted from continuous problem to the discrete problem? So that means when you convert from continuous problem to the discrete problem, now you have to see that whether this discrete problem, if you use again Taylor series or some other things, you should get back the original problem. If it is the case, we can call it as a consistency. So that means that consistency between the continuous problem and the discrete problem. If this is there, that means that if you can convert from continuous to the discrete and from discrete to the same continuous, you can call they are the consistent. How mathematically we can check it in a short duration of the time? So they are telling use just by idea of the local truncation error. Okay, truncation error means local truncation error. So if local truncation error goes to 0, as parameter, there is a parameter. So it goes to 0, then error goes to 0, like local truncation error. Then you can say that the scheme is consistent, isn't it? So that means it will talk about the discretization quality. That means your discretization is perfect. Okay. Now next is the stability. Stability is telling about that the error, whatever error is there, okay, in the system, it is under the control. It is bounded. So two things are there. Your discretization is perfect, your error is bounded. Then Lex has given that your solution always will converge, isn't it? So what is the meaning of the converge? Converge means that the numerical solution will give you the exact solution, true solution. Okay. So convergence means that your numerical solution, which comes from the numerical side, numerical method, and the actual solution, which comes directly by using analytic method or physical problem, if they should match, isn't it? Then we can say it is a convergence. That means converging. That means actual solution is there. If your numerical solution is going and sit on that, you can say that, or maybe close by to that, you can say it is a convergence. So convergence means that numerical solution is same as the true solution, exact solution. That is called the convergence. But directly getting this idea of the convergence is tricky, because you may not able to say that by experiment. You can say, but theoretically it is little bit difficult actually, or little bit a longer way to say that your numerical solution and this exact solution are the same. By table and other things you can identify, but I'm telling about the theoretical point of view. You can do it by using error analysis, you can do that. But if you go through the consistency, you go through the stability, Rich Meyer has said that you don't have to check anything. If your consistency is there, stability is there, convergence is the guaranteed. But it is there for the case of linear. Okay, so that is called the Rich Meyer. Okay, so here the definition again I have written about the convergence. What is the convergence? Convergence, it is written that a numerical method is said to be convergent if the numerical solution approaches to the exact solution of the given PD, okay, as discretization parameter tends to 0. That means if mesh parameter goes to 0, both becomes same. Okay, that is the formal definition of the convergence. Means numerical solution and exact solutions are matching if by the refinement of the meshes, you can understand. That means see that many times in many papers you might have seen it, that they will say that if you are refining your delta x, suppose you have taken delta x first 0.1, then next time you have taken 0.01, next time you have taken 0.001, and you see that when you are refining, finally it is leading to the exact solution. And yesterday I have shown it that Euler's method case, actually for the Runge-Kutta method, I have shown it that on 13th actually, that when you take h.1 Euler method, if you solve a differential equation, it will be little far away. But when you refine it, you take 0.01, 0.001, 0.0001, you see that it will exactly going to sit on the exact solution, isn't it? So that means that it is going to converge. So that is the meaning of the convergence. Now, again here, these are the again renaming of the proper role of these properties. Consistency means that how well the discrete equation approximate the PD. That means that there is a synchronization of discretization. That means so discrete problem and continuous problem are same. Okay. Stability means that it is telling that how well the method controls the error. So consistency is that how well the discrete equation approximate the PD. Stability means that how well the method controls the error propagation, and convergence means that whether the numerical solution approaches to the true solutions, right? So three things if you can ensure in any numerical methods, that means it is the robust number. Okay. So why is convergence is important? We care not just about stability or consistency alone. We want that computed solution should be close to the true solution, because that is our ultimate goal, right? They are the building blocks. Consistency, stability are the building block, but they are not talking about the value of the solution. But convergence is telling about the solutions, isn't it? So that means numerical solution and true solutions are matching. So convergence guaranteed that the numerical method correctly models the PD as mass is refined. So convergence is important because it will tell only that the numerical methods results are reliable. Okay. Not only consistency and stability, but of course, when consistency and stability is there, you can say about that. I'll talk about that through the lexical story. Okay, so now just here I have given the definition of the error. So you see that you can define the error in various ways, like the difference between the numerical solution and the exact solution. We call that this as an error, and there are various types of the error you can define. You can say that in the terms of the maximum absolute error. Okay, or you can say that RMS root mean square error, that is called L2 error. So different norms. Okay, they are the basically estimators. So different estimators you can say, and you can say the error, right? So if you remember that in the class 10 or class 12, you might have done some experiment on Vernier calipers or screw gauge, right? So there you might have seen that when you do the reading, 10 reading, you have done it, and then you see that you can use the RMS or you can use the absolute, right? Accordingly, you will say that how much this particular instrument is having the error, right? Same thing here, it is depending on you whether you are going to calculate the error in one estimator. It's called the maximum norm, or you can L2 norms. By that you can identify the errors. And the order of convergence, suppose you have the error estimate, and the error estimate of this form, I'm again giving a very simple form. So I'm not using the correct notation of a small O or big O. Okay, again, that is there actually, but maybe later if I get an opportunity to give a talk, then I have to talk more about the small O and big O. Okay, but I'm telling here, just if your error estimate has the form that capital C delta x power p plus d capital delta t power q. Suppose it comes in this particular form, so you can say that the order of accuracy in the space it is p, and in the time it is q. Okay. Now again, here connection between consistency, stability, and convergence, isn't it? So again, this is renaming again. I'm again tracking 2-3 times again the same thing. Consistency means LTE, local truncation error, goes to 0, as delta x delta t goes to 0. I have not mentioned, but now you should know because already I have told about that. Stability means that error under the control, and convergence, finally you can say that the global error goes to 0. Okay, not the local truncation, global error, right? So stability is about the error growth, convergence is about the error size. So again, you can rename. Just I try to fill in your mind that stability means connection with the growth of the error because it is a controller. Convergence means basically the actual solution is meeting or a numerical solution is meeting with the actual solutions. So that means the error becomes smaller and smaller. Okay, so error size that depend that suppose error is there, then you can say that the convergence happening with under this error, right? Even if the method is consistent, if it is unstable, Okay, this is important. You look at this line. Okay. So if you look at this line, if method is consistent but it is not stable, means it is not stable means unstable. Error will grow and destroy the convergence. So convergence may not be guaranteed. It may or may not be there, isn't it? So both should be there. And how to ensure it that? That is called the Lax equivalence theorem. Lax equivalence, Lax Richmeyer actually, he gave the result actually. Okay, he has proven it in his paper that if you have a linear PD, please note that again the condition is there. This result is there only for this linear. Linear should be there. I forget actually. It should be linear. Consistency is different. Linear should be linear. If you have a linear, consistent finite difference method for solving well-posed linear PD, stability is the necessary and sufficient condition for convergence. That means consistency is there, stability is there, convergence is guaranteed by Lax. So you don't have to show the convergence, but provided your method or your problem or your equation is linear. If it is not linear, we can't say. Please note that Lax equivalence theorem is applicable only for linear partial differential equations. If this is not linear partial differential equations and you got the consistency, you got the stability, there is no guarantee about the convergence. It may be there or it may not be there, isn't it? So how to do for the non-linear problem? Again, this is a big lecture. The convergence of a non-linear problem, there is no straightforward way. There is no direct theorem or there is no direct results which tell about the convergence of non-linear problems. It depends on the numerical, isn't it? So you see that I have again mentioned that Lax theorem is strictly valid for the linear problems. For non-linear problem, stability and consistency important, but does not guarantee about the convergence. So we need some more information. We can use maximum principle, of course, there. Even maximum principle help us actually there to make the monotonicity. Okay. So you can use monotonicity of the solution, energy estimates, entropy conditions. Okay. Or you can energy estimates or error estimates, you can say that error estimates in an energy loops. Okay, so through that you can establish the convergence. Yeah, and the energy estimates means that error estimate actually in energy loops. Okay, yeah, L2 norms or Ln norms that depend on which energy loops. So that is a no, that actually generally you see that this is commonly used in engineering problems because you see that when you have any system, right, when you solving it by any method, whatever energy is there in that system, it should be preserved. So that is the reason, nothing else. So engineering problem, they won't call this like this. They will use this energy word. Yeah, correct. So there should not be any dissipations and all, right? Yes. See, actually, when you talk about the Fourier series and Fourier transforms, it's again interesting there actually. When you have a signal and you are converting signal from time domain to the frequency domain, isn't it? And actually, we are using this in our communication devices. And when you convert from one domain to the another domain in a system, okay, and pretty good thing with the Fourier analysis is that when you convert from time to frequency of frequency to time, the energy of the signal, that means signal is nothing but the function, is always preserved. So these are the names actually. See, if you go to the mechanical engineering, they will talk about all these things. They won't talk about that it is a temperature. They will say that this is the heat evolve in the system through the temperature. They will use this nomenclature. But if you are in the mathematics department or mathematician, you will talk about the solutions. They won't talk about the solution. They will use the more physical names. Suppose if you have a Newman boundary conditions, they will say boundaries, right? If suppose your Newman boundary condition equal to 0, they will say boundaries are insulated. So all these things they are using it, which we may not be that familiar with it. So it depends on the context we are using it. So that's in that way it is written. Entropy again. One can talk on entropy for 1 hour or more than 1 hour. It's called the randomness. Because non-linear problem is there is no straightforward way to check the convergence. So depends on the problems, depends on the method. Accordingly, you can proceed. Okay, now we want to move to the next topic, von Neumann stability analysis. Von Neumann stability analysis is a very popular analysis actually to make sure that this particular system is stable. So till now, whatever we talk about it is stable or it is not stable. But question comes, how to check whether it is stable or not, right? So how to check whether it is system is stable or not, especially the numerical system, which comes through the partial differential equation discretization. So you can ensure that by using a matrix method, which you have already done it. You can use maximum principle also, but there is another way, which is again a very precise way to check the stability conditions or stability of the system by using the von Neumann analysis. Okay, so now I just try to give something about this history that when stability analysis people start talking, isn't it? So the need of stability analysis arose with the invention of finite difference methods in somewhere 1920 to 9. The numerical methods are not very old, though Euler has given the idea, but it was not used because the hand calculations, people are not feeling comfortable, so all those things. So basically started not very long, actually you can say that 150 years back only people are using this numerical methods. And this stability things started, it is as per history is that 1920, in the middle of 1920 to 1940. Actually, von Neumann has given his stability theory in the 1940. And there is again, if you look at that, there is a book actually, Introduction to Numerical Analysis by Atkinson T. Kendall. Actually, you can see in that book, they have mentioned, I think, some example of US, especially the oil reservoir and all. So just by small mistake in the calculation, actually they lost a huge amount of the money and they wrongly dig the place where the oil was not there. So these things came in the picture after that, actually, when some mistake happened and people found that there is some mistake in the calculation, we have not proper taken care of the round of error and other things. So that is why it happened, actually, especially when you see that I came to know from an ISRO scientist that when they take the value of the pi, right, and they will take care of the value of the pi in such a way that up to 14, 15 digits decimal places. And if they want to use 22 by 7 something, they have used something different. So, but why it is so? Because if a small error is there, isn't it? And if numerical system is not very robust or very stable, isn't it? There is a high chance that it will give you the wrong results, isn't it? So, and also a lot of money involved. So they want that at least simulation should be perfect. Okay, so early numerical simulations encountered severe instabilities when discretizing PD. That means we don't know. Sometimes it is working, sometimes it is not working because we are not unsure about the stability. Okay, so, but before that, it is written that 1928, basically, three people, you might have heard this name several times, Richards, Courant, and Friedrichs and Levy, right? So three people, Richards, Courant, and Coates, Friedrich, and Hans Levy. These people establish a condition for hyperbolic PDs, and it is known as the CFL condition. It's very popular. All stability conditions, we call them as a CFL condition. Okay, so they were the before the von Neumann stability analysis. Okay, so showed that important time steps can be cause blow up even if discretization is accurate. Even though discretization is perfect, but still you see that choosing the time step is very step size. Actually, time steps means time step size is very, very important. So that is the thing they have analyzed, and then it has come to the general people or scientists. In front of scientists, they might have put these needs, and then people start working. So you know that this person, von Neumann, actually, I don't exactly remember his date of birth. So basically, he was an Hungarian mathematician, but he worked mostly in the US. So he actually gave this idea of the stability. I think I forgot to write. It is here. Okay, it is there. So it is here actually. So John von Neumann, actually, mostly people will pronounce this V as a fa. So they will say John von Neumann, but we call that a John von Neumann. So 1903 to 1957, he has developed this method, von stability analysis, in 1940. Okay, this I'm telling you so that you will more connected, isn't it? And interesting thing is that if you Google this name, Manhattan Project, so very popular projects actually. Okay, in that project actually he developed this stability analysis for simulating hydrodynamics of nuclear explosion. So because actually this analysis has not come just from a mathematician point of view. Actually, it has come to study the hydrodynamics of nuclear explosion. This project itself is interesting. Yeah, correct. So here actually this need to ensure the stable numerical methods for nuclear bomb and detonation models. Okay, and this handle error growth due to the small perturbation and round of it. That already we know that, because once it is stability, we can call about all these things. And the key contribution here is that they basically write the solution or the error in terms of Fourier series. See that the Fourier actually has given Fourier series long before this 1940. Joseph John Fourier, he basically a French mathematician or physicist. Actually, he has given the Fourier series long back, and his idea of giving again Fourier series is very interesting. He has given the Fourier series not for anything else. He was solving a problem. Okay, you can call that as a heat equation for current. And experiment things he matched with the theoretical things. That means experimentally he got the temperature at certain points, but he was not able to find the theory behind it, right? So he wanted to solve the heat equation, but he was unable to solve it. And then he himself developed in a series, which is known as the Fourier series, just to solve that particular problem, isn't it? But later people identified that it's a wonderful thing, and now you see that a lot of courses are there on that in our electronics department, electrical engineering department. All electrical signals they will try to write in this particular fashion. Here, one new composition of the errors which are there in our numerical system, okay, or the solution can be written in terms of the Fourier forms. And now it becomes very standard stability. This is very standard stability tool actually people are using. Okay. Now why Fourier modes actually? So again, the reason is that if you want to capture a small error, you can write in terms of some known functions, and the simplest known function maybe in his mind, but click that we can use the Fourier series. So what the correct one, but as per analysis is working, it is similar. Like if you write this form or you write the error form, both are the same, isn't it? So don't confuse. So here the initial error can be decomposed into the sum of Fourier modes, and this is the basically Fourier series. If you remember that the Fourier series, it is written in terms of the complex forms. Okay, there are two forms of the Fourier series. One in the form of sine and cosine. This is called the real form. Another is the complex form. Both basically, mathematically, both forms are equivalent. But practically, there is maybe some difference, but mathematically, all both are the same. So here they have used this complex form of the Fourier series. So they mention about this, and this particular things they have written that with the trial solution of the numerical scheme. So this is solution. Actually, you can write g power n. N means nth time label. Okay, and exponential of I means that it is the square root of -1. K is the wave number. Okay, J is the, this is the special time step, jth time step. So basically, this is xj. So xj means that xj means actually j times delta x. That is what is mentioned. And this is called the amplification factor. G is called the amplification factor, this one. And he has identified that this method is stable because this is the error actually. Here I have written U form, but basically, because when you have a numerical method, suppose UN plus 1, I'm just writing minus UN. And I am writing that this is the true solution. I'm writing UN plus 1 minus UN. And when you subtract it, you will get n plus 1 minus En. Isn't it? So in many books, there rather than they have written like this. But I have written UJ, so you don't have to convert in the error equation directly. Practically, you can use it. Because if you look at that, both are the same. Isn't it? So what he has thought that this error, if we can write in the form of the Fourier modes or by using the Fourier series, then what is the benefit of that? But benefit of that is that basically error you have given in the oscillation form, so like a sine, right? And now you will analyze that what is the growth of this error, isn't it? Because it is easy to analyze in the waveform. So when you analyze and you see that if you look at the sine and cosine waveform in the Fouriers, actually you look at that amplitude, right? Amplitude. So you see that wave size will be depending on the amplitude. If wave size is not going to be uncontrollable, that means that it should be under control. It should be under control means that the wave length should be less than 1 because all the time it is increasing multiple times. So g power n. So g power n will be under control if as n goes to infinity large, only when the modulus of g should be less than 1. So modulus of g should be less than 1 means that your error is under control. Okay. That means it is going to decay. Isn't it? So that is the idea here. So here it is used. Okay, so now let us do this von Neumann stability analysis for heat equation. Now heat equation you can, why I have taken that again, it is the simplest form. You can make various schemes. So you can use here, here I have used here FTCS. FTCS means that forward in time, center in space. That means the derivative with respect to time is approximated by the forward difference. Okay, basically again it is interpolating formula. So forward difference we have used this for making the time derivative approximation, and for the special derivative, that means this we have this actually we have used here forward difference, and this we have used here central difference, right? Like that. Here you can say that it is basically time. So it is J, so it is used, isn't it? Forward time. So forward time. So n plus 1 to n, right? So it is like that. So this scheme has come up. If you do it, I think because already you have done the courses, so you know that this is a popular FTCS scheme. Okay, directly I try to write. Okay, I have not made any this because already you know it, right? So this scheme is, can you type it that whether it is explicit scheme or implicit scheme? Can you type it that it is explicit scheme or implicit scheme? I want that at least some people should write it because you have done the course, right? Whether it is explicit scheme or implicit scheme. Okay, this is basically explicit scheme. Why it is explicit scheme? because you can find out this is actually something like that. Whenever you have a doubt, you can put these two lines. First at the nth time label, another one is the n plus 1th time label. So look at that. If I'm putting these 3 points, so this point is connected with the j, previous one j minus 1 and j plus 1. So you see that there are 3 points here, and at the time label n plus 1 only 1 point is there. Okay, this is called the computational molecule or stencil. So you see that if it comes like this, it is explicit scheme. That means you can find out this is unknown. N plus 1 is unknown. So you can find out the unknown, okay, without any problem directly. So that is why it is called explicit. Explicitly, you can find out all unknowns values. Okay, or if you want to remember it in a simple way, that if there is a one point or one molecule or one node, whatever you can call, okay, in the computational molecule or in the stencil of the numerical method, this is actually numerical method, it is the computational molecule or stencil. If there is a one point at the advanced time label means n plus 1, then we call this as a explicit scheme. If there are 2 points or more than 1 point, I can say, then it is called implicit scheme. So this is explicit scheme. So explicit scheme is always very convenient to programming point of view, for writing point of view. In all the sense it is convenient. Now let us see, we want to analyze the stability of this scheme. So we can use this, okay, von Neumann stability. So you just write it here in this form and then substitute here. If you look at that, we have written that u and j equal to g power n e raised to power I k and j delta x. Okay, so whenever if we want to make use of the n plus 1, then nothing will change. Here it will come n plus 1 and remaining thing will be the same. If you write u and j minus 1, then g power n will be same, e raised to power I k and then j minus 1 delta x. Like that you can make it, right? So that is what it is written. So I think that it is very clear to you. It's a small font, but it is clear to you. Nothing actually, directly we try to write, okay? And what about the r? Can you write what is r? R is your delta T by delta x square, right? This is your r, because you know that this r, it comes from the discretization. Okay, so when you just look at this, now g power and you remove it, so you will get in the left. So the value you use the Euler formula e raised to power I theta is equals to cos theta plus I sin theta. In that case, this will give you the 2 cos k into delta x. I think this is simple trigonometric form. And then g becomes 1 minus 2r, 1 minus cos k delta x. And now if you use again trigonometric formula, okay, like a cos 2 theta is equals to in terms of sin theta by 2, then you will get this. You got this. I think that this is a very simple one. It is just normal mathematics. Now we need to apply the condition that modulus of g should be less than or equal to 1. So that is important now. So what happened actually? 1 minus 4r sine square. Okay, I'm writing just theta. Okay, less than 1. This should be there. Now let us see that what will be the condition on theta or maybe r. Let us see. So that can be written as minus 1 is less than 1 minus 4r sine square theta is less than 1. Okay, you know that mod of x is less than 1 means that x should be between minus 1 to 1. So if you look at the two limits are there, so let me take the right hand side. So 1 minus 4r sine square theta should be less than 1. Okay, and this is true for, so what does it imply? It implies that minus 4r sine square theta is less than 0. And you know that r is always positive, sine square theta is always positive, and it is true for all r. So this inequality is true for all r and theta. There is no problem. Now let us take this inequality. I am now taking another inequality. Now I am taking this inequality. If I take this inequality, you see that here we can say -1 is less than 1 minus 4 r sine square theta. So how does it, like we will write? So we can write 4 r sine square theta is less than 2. Okay, by adjustment of these terms. And then you can say that from here that 4, or let us say r sine square theta is less than half. Okay. And if it is the case, sine square theta is always positive. So you know that the maximum value of this is like this. So I can say that the maximum of sine square theta should also be less than half. And you know that it is always r sine square theta maximum value is r only. So r is less than half. So from here you got the condition that r is less than half. Okay, or equality. Sorry, here equality is there. You can put the equality. I put that in equality. Actually, it should be inequality. Equality will create problems. So I suggest that you can consider this as an error actually, because equality may not reduce the error, isn't it? So take r is less than half. So I suggest that you make this change. I will make the change when I will send you the slide. So rather than using this, better to use this here. Less than 1. Equality should not be there. So r is less than half. Equality don't need, because equality may lead to confusion. So r should be less than half. I'll make correction. Okay, so r is less than half. That means delta t, again equality here, because I made this error. So here also it is there. Okay, so r should be less than half. That means delta t should be less than delta x square by 2. So please note that if you choose your step size in this way, then this particular explicit scheme, which is known as the FTCS, will give you always the stable solution. That means the chances of error growing is almost nil. But if you use equality, there is a chance that it may not grow. Error may not decrease. So error will decrease when it is less than 1. If it is 1, it may not grow, but it will not decrease. So it is here already there that it is written that marginally stable. That is the reason it is written like this. So G equal less than 1, like stable. G equal to 1, it will not decay, but it will be same, like marginally stable. But I suggest that I will remove this equality. And G greater than 1, that it will grow, error will grow, and then method may be unstable, okay, or unstable. So instability will be there. Now similar things you can try for the another numerical method. It is known as the BTCS, and the full form of BTCS is backward time central difference. Okay. Central difference in space. So backward time. So if you use that scheme, you will be getting this. So what is the difference actually here? You look at that, the difference in the explicit and implicit is that earlier you are having a molecule like this and this. Now here what is happening? Here it is something like this. Basically, with the help of 1, you are calculating 3, isn't it? So it will lead to the system. So that is why BTCS is known as the this is an time level, and this is n plus 1. So this is the BTCS, and so actually BTCS. So this is implicit scheme. So implicit scheme, explicit, otherwise implicit. Yes, this one is implicit. So implicit scheme, that means that you cannot find out the un plus 1 directly. So you have to use now system of equations. So you have to use something like ax equal to b. Through that you can calculate the solution, isn't it? So this will use more computational effort compared to the FTCS. FTCS, you don't need much effort, but here you need the effort, isn't it? So solving this is always computer is required. Otherwise, by hand it will take a lot of time. But FTCS you can do by hand calculation also. So computationally, FTCS are need less effort, but BTCS needs more effort, or explicit needs less effort, implicit needs more effort. But again, plus and minus things are there. Okay, then we will see one of the plus and minus thing, which is stability. Again, if you use the stability from von Neumann, write in the Fourier modes, and then if you put all the values, okay, we put all the values here. So again, it will come like this, and then yeah, you will get like this. I am not sure it's correct or some error is there, because it is n. So here it will come n plus 1, n plus 1, n plus 1. Here it is n, right? So, okay. Left hand side will be G will be with this all, and then right hand side will be this. Left hand side will be this. G is multiplied with everybody, like here. You see that it is actually multiplied with everybody. So I think we should put the bracket here. The mistakes actually. Here bracket should be there. So this is for all, and this is this one. Then you will be getting it. I think some error is there. GIK delta X, GIK, K, yes. So what you are going to get actually, you will be getting here. This will be like this. G will be here. So 1 times, right? And then use the formula of everything. You got from here this form. I think some error is there. This is my calculation error. Final result is correct. Final result is correct, but I think somewhere something is missed here. This actually, this result is correct. This result is correct, but here somewhere this calculation got missed actually. So everything is a, you can calculate that G is equals to 1 by 1 minus whatever it is there. Okay, this one comes. Okay, so this is not correct. This will come, and finally, this result. Sorry, this result is perfect. See that sometimes no one don't care about that. It is correct. Okay, I will rewrite it and I will send to you. This actually, it is typing mistake. So this will here everywhere G will come. So this will come down. Okay, remaining things are fine. So here it will be 1 minus something, and then it will come G equal to 1 by 1 plus 2R 1 minus cos K delta X. Okay, and then you use trigonometry and you will get this. And this is always less than 1. Does not matter whatever it is R, because you look at the denominator. Look at this denominator, 1 plus 4R sine square K delta X by 2. It is always greater than 1. So the modulus of G is always. So if it is less than 1, then it is stable, does not depends on the R. So this scheme is stable for any R. Okay, any R. And R is always positive. So you can say that it is any R, it is white. Okay. So the conclusion is that here PTCS is unconditionally stable, while FTCS is a conditionally stable. That means for backward time and central difference, but as implicit schemes, they are stable without any condition on the R. If there is no condition on R, that means there is no condition on time steps. Okay. While FTCS are having the condition on R, which is less than half. Okay. So of the implicit scheme, not most actually, all implicit schemes are unconditionally stable for the linear system. This is just written here that high frequency Fourier mods are more strongly damped because of this, but it is okay. This is not required, so just it is enough for you. I will send you. You can go through that. Okay, next scheme is the Craig-Nicholson scheme. Have you heard the name of Craig-Nicholson scheme? Please type. Have you seen this Crank-Nicholson scheme? Okay, very good, Nikhil. Fine. So, Crank-Nicholson scheme, can you tell that it is implicit scheme or it is explicit scheme? Very good. It is implicit scheme, right? Okay, it is implicit scheme. So this scheme is little complicated. Okay. And I'm not going to teach the scheme, just I will draw the computational molecule. It is something like this. This is n, this is your n plus 1. So you see that 3 points are here, 3 points are here. j minus 1, j plus 1. So you see that these are there and these are there. So it is implicit scheme. It is better than PCS in terms of the implicit, but again, it is more complex than the implicit scheme. Okay, when you use the Fourier and all, so you will see that, I think this is correct. You will get, this is the amplification factor. And this amplification factor again, basically is always less than R. Sorry, less than 1. If you take the modulus, it is less than 1. Then again, I can say that this implicit scheme is unconditionally stable. Okay, so I would say that take this as a homework whenever you are free. You can try yourself. This scheme is there. Okay, and take the Fourier modes, right? Von Neumann stability Fourier modes. Okay, put every value in the scheme and check that whether are you getting this G or not. I have not put all the steps. You can try yourself. Okay, and you will see that you will get this, and the modulus of G, you can say from here, is not is always less than 1. It does not depends on the R. Therefore, it is unconditionally stable. So again, it is unconditionally stable. So overall, what is the conclusion here? If you have a FTCS, you have the BTCS, and you have the Crank-Nicholson. These three. So this is conditionally stable. This is your unconditionally stable. And this is again unconditionally stable. But if it is, you see that it is explicit, and this is your implicit, and this is again your implicit. So implicit scheme is for heat equation, you have seen that are unconditionally stable, and explicit schemes are conditionally stable. But again, in terms of the use, explicit schemes are comfortable, less computational efforts are needed, while BTCS or CN, they are the implicit schemes, more computational efforts are needed. But plus point is that they are not depending on the, they are unconditionally stable. Their time step size is not restricted. But if you want convergence for FTCS, that R has to be restricted. That means delta T should be less than or equal to delta X square by 2. So it is restricted. So explicit schemes, less computational effort, but delta T is restricted in order to get the convergence. BTCS or CN or implicit schemes, they are computational costly, but their time step is not restricted. So every scheme has its own plus. You can't say that explicit schemes are good or conditional stability is good and conditionally stable. Yeah, that's true. I'm not talking about the order. Of course, Crank-Nicholson is in better in order, isn't it? But again, Dr. Nikhil, if you look at that, when you do computationals, actually, you will see that though it is computationally higher in order, but the cost which you are making here, like the effort you are making here, is not justifying that much order. Practically, I'm telling is that you may feel that BTCS may give the better results, okay, compared to the Crank-Nicholson, because again, here that order is something like delta x square plus delta t square, right? So if your delta x and delta t is small, then only it will have a sense. If it is not small, in that case, you may not feel that much higher, because BTCS will give you the order something like that delta x square plus delta t. Crank-Nicolson will give delta x square plus delta t square. So delta t square will be effective if delta t is sufficiently small. Otherwise, delta t and delta t square may be similar. Not much difference, right? So, yeah, so actually, but you don't want actually, because simplicity scheme has the benefit of unconditional stability. So that means we don't want smaller delta t. So for example, if you don't want a smaller delta t, you may see that BTCS has less computational effort and less chances of the round of accumulation. So you may see that it's also giving at par with the Crank-Nicolson. But theoretically, of course, CN is much better, isn't it? So again, these are the questions of debate or question of experiences, isn't it? Please don't think that I'm favoring BTCS, I'm not favoring CN. These all are matter of experience, problem depending, and requirement, isn't it? So we can't say that. These are analysis actually you will only when you do hands-on computations, you will realize all these things. But of course, as far as von Neumann is concerned, it's a wonderful tool. Actually, it will tell us about the how the error is growing, how to make that method is stable. Oh, okay, for these heat equation and all, it is fine. But suppose you're solving a problem which is not in a regular format. It is a convection diffusion problem, or it is some other problem, isn't it? And you want to analyze the stability, which is not in the standard form. Then in that case, if it is a linear, you can work with the von Neumann and you can ensure that stability is there, isn't it? So this is a wonderful tool given by the von Neumann. Make use of the Fourier modes, okay, to analyze the stability of the numerical methods. Again, some error is there here. I will make correction and I will again give it to you. Okay. Before giving, I need some time to make some corrections. So I think from my side, I am done it. Actually, I finished it. Okay. And this stability analysis you can extend for the wave equations also, isn't it? But this stability is not there for the time independent like Laplace and all, isn't it? So stability actually is not needed there. They have different things, isn't it? Because there is no time in the case of Laplace, isn't it? So Laplace kind of problems, Poisson kind of problems, when you discretize it and solve it, you don't need stability actually, exactly this side. So you can go to use the maximum principle. Through that, you can predict about the solutions boundedness, and through that you can say that the error is bounded and it is not going to grow because there is no time. So problem comes only in time. So time dependent problems are controlled way is given by the von Neumann. So von Neumann analysis is there only for the time dependent problems, for parabolic and hyperbolic, or problem which is similar like the heat equation or similar like the wave equations, or any time dependent problem. Von Neumann will work, but again, the stability from the von Neumann is reliable only for the linear system. It is a non-linear system going to be big challenge actually, even using the von Neumann, isn't it? Fine. And generally, if it is a non-linear problem, we don't prefer the stability like this, because why we prefer for the linear case? Because Lax equivalence theorem is there, because final goal is the convergence. So for getting the convergence, we are trying through the consistency and stability. But Lax equivalence is not there for non-linear case. So why we will go for consistency and stability? So directly go for the convergence by using energy estimates or entropy conditions. So that we will try to get it. Okay. We will do only for the linear case. Okay. But if non-linear case, a lot of research people are doing by making non-linear problem as a locally linear problem, and then they are using stability by using von Neumann, consistency, and they are using the Lax equivalence theorem, that they have considered the non-linear problem as a local linear problem. Okay, and they say that this analysis is there for the local non-linear problem, so it may work for the global non-linear problem and supported by the numerical results. This is all the research problems. But as for theory is concerned, it is for the linear case. So I'm finished. I'm done actually. If you have any question, you please ask me.
Participants, if you have any question, you can ask. You can write on the chat box.
So I will actually, there are some errors in the slides. So which I have identified when I was taking this class, and I will correct it, Rahulji, and then I will send to you.
Yeah, okay. Yes, sir. No, sure. So if there is no question, let us thank to our speaker, Professor Ashish Avasthi ji. Some Dr. Nikhil Srivastava on the chat box writing no questions, sir. Wonderful lecture, sir. Okay, that's good. Thank you, Dr. Nikhil Srivastava. Thank you. Okay, the RK Binda, thank you, sir. Always a pleasure listening to you talk, sir. Okay, yeah. So I'm
Rahul,
sure.
actually, just I want to know that there is one participant, Brinda RK. I think she worked in our department. I think so. I don't know. There was a one. Okay, okay. Fine. Yeah. Fine, Brinda. Okay, nice to see you.
Yes, she is writing. Yes, sir. Yeah. She knows.
Yeah.
Yeah, she was attending.
She is associated with us since long. My all students all are aware with Brinda.
That's good. That's good. So it's always good to have our earlier students in our talk. So it gives a good feeling also.
Yeah.
Yes. So everybody is appreciating your lecture, sir. They are writing on the chat box that it was a very wonderful lecture.
Thank you so much.
Yeah. So thank you very much, sir, for being a part of our FDP. Your all three lectures were wonderful, and candidates, I'm sure they must have enjoyed your lectures. And now, participants, we can take a break of let's say 5 to 8 minutes, and then we will again meet here at 12 p.m. and another lecture will be by Professor S.K. Rajput, Professor Sarvesh Kumar Rajput from IST Thiruvananthapuram.